What's up, everyone? Welcome back to Speed, Math, and CS. So today we are going to be resuming our study of AP Calculus AB, and today we are going to be looking at the applications of derivatives. So if you remember last lesson, we were covering things such as like the derivative rules, how you find derivatives, and we briefly introduced related rates. So for this class, what we are going to do is we are going to look at essentially what we are going to do is we're going to look at the application of derivatives. So we are going to be taking our knowledge of derivatives that we know previously, right? And we are going to be using that in order to solve more like application-based problems, right? So yeah. So first, let's start with a little bit of review of implicit differentiation, right? So recall that if we have a function like so, x plus y equals to 1, right? If you have something like so, a function like so, right? The derivative of this, we take the derivative of x, right? The derivative of y is dy over dx. And the derivative of 1 is equal to 0. And then we would solve something like this, right? This is implicit differentiation. But let's say we now have let's say we have x, y equals to 1. Like this is very simple, right? And we want to find the derivatives with respect to y. So essentially what we're going to do here is we're going to use product rule, right? So the derivative of x is just 1 in this case. So it's just going to be y plus x times the derivative of y. The derivative of y is just dy over dx. So it's going to be x dy over dx, right? Equals to 0, right? And of course we can solve for dy over dx from here, right? So now essentially actually let's actually go through how we solve for so we will we have something like this, right? So essentially what we are going to do is we can essentially we have to isolate dy over dx. So it'll become y over x like so. And y, if we simplify y out here, right, we simplify y equals to 1 over x, right? So essentially this is essentially going to be negative 1 over x squared, right? And we would get the same thing if we just directly took the derivative of y. So implicit differentiation, it essentially involves differentiating all variables, right? So for example, if we were just taking the crude derivative of something like dy squared, right, we would treat it just like chain rule, right? So chain rule will tell us, right, that we can essentially, if we have a function that's being encapsulated inside of another function, we can essentially take the derivative of that with respect to the encapsulated function and then multiply by the derivative of the encapsulated function. So in essence, we can substitute some u, and then take the derivative with respect to that variable, and then we can take the derivative with respect to x, right? So in this case, if we're trying to find if we're trying to find the derivative with respect to x, right? So if we're trying to find this, right, the first thing we know that this is equal to finding the derivative of y with respect to y multiplied by finding the derivative of y with respect to x. So if we start with finding the derivative of y with respect to y, right, simply all we have to do, right, or actually in this case, let's say 2y squared, let's say we define this as u equals 2, right? So essentially, the derivative of u with respect to x is equal to the derivative of y with respect to, no, the derivative of du with respect to dy, derivative of u with respect to y multiplied by dy over dx, right? So essentially all we have to do here is we can say u, in this case we've defined a u, right? But like u prime will then be equal to 4y, right? And in this case, because we have to multiply dy over dx, right, we would multiply that out, like so. So this is how implicit differentiation works. So in the last time, we introduced a thing called related rates, right? Which essentially means we are going to use implicit differentiation and things that we are given based off of, we are going to use information that we are given based off of like the problem itself. So one, and then we're going to use that in order to find another derivative, right? So yeah. Sorry, whiteboard is so laggy. Yeah. So we'll label this as, this is problem number 1 of the day, right? This is problem number 2 of the day. I'm gonna continue, at least for calculus, with the style of we're gonna do problems in the fact of this, where we go and introduce concepts, right? So then now if we're going to problem 4, right? Problem 4 is essentially, we were given a cone like this, right? Like this. And then we have water, right? We have some water that is filled in here, and it is draining. It is draining at some rate, right? So essentially what we know is that the radius of this whole cone is 3, and then the height is 6, and then we're asked to find we said that the rate of the height is negative 2 meters per second, right? So it's losing 2 meters of height per second. And we were tasked with finding the rate of change of the volume at height equals to 3, right? So in order to do this, right, what we would do is we would take the actual like formula for a cone, right? So it's going to be V equals to 3 pi multiplied by r squared times h. R squared multiplied by h, right? And then with this, essentially, we now have a thing where we are going to essentially, so v equals to pi over 3 r squared h. So then what we'll do is we'll take the derivative of this, right? So dv, we'll take the derivative with respect to t, right? Because we're trying to find the derivative with respect to time. So we'll take dv dt equals to pi over 3. Pi over 3 is a constant, so it'll be fine. So then now this, in this case, we have a product, right? So this essentially will go inside of a big thing, right? So it'll be like this derivative of r squared is 2r dr over dt. And then the height, essentially, so the height is essentially going to, the height is just be here, because we're using product rule. And then plus r squared dh over dt. And then what we are going to do next is we are now going to plug in all the values here, right? Because so our goal is to find the rate at which the volume is decreasing, right? And dv over dt is going to give us that. So what we are going to do now is we are going to plug in all the values, right? So if we plug in all the values, right? dv over dt equals to negative pi over 3, right? If it says the height is currently 3, right? So which means that the radius is going to be 1.5, because the radius is always half of the height. Because if we take a cross section of a cone, it's a triangle. So we can relate the radius and the height are directly proportional, right? So 2 times r, well then it is just a height. So the height is going to be 3 and multiplied by 3. So this is going to be 9, right? Multiplied by, what is dr over dt? Because the height is decreasing at a rate of 2 meters per second, right? The radius is going to also be decreasing at a rate, but at negative 1 per second, because the radius is always half of the height. So it would be negative 9 plus, oh, I don't know why I put a negative out here. There's no negative. It's just regular, right? But then, essentially, and now we add r squared, right? The radius is going to be 1.5, right? So 1.5 is squared is 2.25. Multiply that by dh over dt, and that is going to be negative. We're multiplied by negative 2, right? And this is going to become negative 4.5. So if we overall simplify this, right, we're going to get, if we divide this 3 out from here, right, negative 4.5. So it's going to be negative 4.5, negative 4.5 pi is going to be dv over dt. So the volume is decreasing at a rate of it's decreasing at a rate of 4.5 pi meters cubed divided by seconds. So this is our first derivative application. So derivative application number 1 is going to be related rates. So now let's move on to the next application of the derivatives. So the next application of derivatives, we are going to be talking about finding extrema on an interval. So this will be local extrema, and so we're going to be talking about local extrema, and we are going to be talking about we're talking about local extrema and absolute extrema, right? So the minimum and maximum of a function on an interval are extreme values, or extrema, right? The concept we'll be using of the function of the interval, right? The minimum and maximum of the function on an interval are also called the absolute minimum and absolute maximum. And extrema can occur on interior points or endpoints of an interval. Extrema that occur on the endpoints are called endpoint extrema, right? So, and then the other thing is, so essentially what we are going to be used to solve this is what we call the EVT, right? So EVT, and we've already learned the MVT, mean value theorem, or IVT, intermediate value theorem, right? Whereas if we draw a thing between 2 points, right, it's going to pass through the middle of the two, right? So that is the IVT. Now we're going on to the EVT, which essentially says that if we take 2 intervals of a function, like a, and then we take another interval of the function b, like we take two endpoints like this, and then we take a function like so, then, so if you take a function like so, right, then f has both a minimum and a maximum on the interval. And these local minimums and local maximums are either like a or b. And these are what we call the critical numbers, right? So they're either a or b, or they're where the derivative, so f of x is equal to 0. This is the set of all possible extrema, is a or b, or where the derivative of f is equal to 0, right? So So the EVT only tells us of existence, but this is enough to show us essentially what we are going to be looking for. So these are what we call the critical numbers, right? So now let's do practice problem number 5, right? So, and typically for these problems, you may be given a graph, but you also may not be. So for the sake of this, just to prepare you for the AP exam, we're not going to, for the most part, when it's not necessary, we're not going to be doing graphs because we need to practice actually doing like the fundamental thinking process without having to look at a graph and estimate on your own, right? So for this, right, for problem number 5, let's say we're tasked with finding the extrema of this function, right, x squared. We're tasked with finding the extrema of this function on the, we're tasked with finding the maximum value of this function, maximum and minimum value of this function between 0 and 2, right? Between this interval, we are tasked with finding the maximum and minimum values. So let's start by finding our critical numbers. So our critical numbers can be 0 or 2, right? So 0, 2 are already in the set. So let's start by, essentially what we'll start by is we'll start by making the set. So something like so. So 2. And then now we must see where the derivative equals to 0. So we must see where y prime equals to 0. Or in this case, if we find the derivative, take the derivative of this, 3x squared minus 6x. Something like so. And of course, we can factor this into 3 times x minus 2 x. So we get once again that the derivative is only 0 at 0, 2. So in fact, we don't have any new values, so we can just close this, right? These are our only critical numbers. And essentially what we do after we find the critical numbers is we take all the critical numbers and we see which one has the maximum value and which one has the minimum value, is the absolute maximum and absolute minimum on that interval, right? So y equals to x to the third minus 3x squared, right? So all we have to do is we just have to plug it into this function, right? And I'll actually save you the time for doing this, right? But if we plug this into the function, if we plug in 0, we'll see that this term becomes 0, this term becomes 0, so the whole thing will be 0. And if we plug in 2 here, 2 cubed is 8, minus 3 times 2 squared, which is 12, so this will be negative 4. So thus from this, we know that on the interval 0, 2, f has a relative maximum, has an absolute maximum at 0, 0, and a minimum at 2, negative 4, right? So the thing is, right, so this is essentially how it works, right? So this is how, if we're given an interval, this is how we're going to find the absolute maximum and absolute minimum. But now let's talk about relative minimums, like relative maximums and relative minimums with problem number 6, right? Yeah, this is problem number 5, so this will be problem number 6, right? So in this case, what a relative maximum or relative minimum means is that it is essentially where a point on the graph where it is at a relatively high point or like a hill, and then the relative minimum is at like a valley or a relatively low point. So essentially what this means is that if we take a hill and look at the two values like beside it, right? Of course, this isn't very rigorous, but you can also kind of see how the rigorous definition would look for a hill and for a valley, right? So for a hill, right, the 2 points around it will be lower than the hill, and the 2 points around the valley would be greater than the valley, right? So the way that we are going to look for in fact, in this case, we have to extend this theorem that we covered earlier, right? This theorem, right? So now we can open up the set with a new thing, because at a sharp turn, right, we could have a graph where the sharp turn is actually the bottom, or it could be a relative, right? So Additionally, when f prime of x does not exist, right? When f prime of x doesn't exist. So this can be something like this, right? So if our graph looks like this, like the absolute value graph, then the relative minimum is at a point, right, where the derivative isn't 0, but rather it's a sharp turn and the derivative doesn't exist. So we have to look for parts where it doesn't exist as well. But now what we are going to do is we are going to look for places. We are going to essentially look to how we evaluate relative extrema, right? So relative extrema, the way we find this, right, is by using a thing called the second derivative test, right? And here's where I tell you that second derivative essentially measures the concavity of the function itself, right? So given a bunch of points where the derivatives are equal to 0, right? You can determine which one 0 or don't exist. You can determine a list of points where, so you can determine a list of values as to where the function will have relative minimums and relative maximums using the second derivative test. So first thing you want to do, and of course on the actual AP test, it's important that you do a sign chart. That is the best way to essentially describe this on the actual AP test, right? So we're actually going to write using a sign chart, but essentially what we are going to do, right, is that let's say we have a function y equals to x squared minus 2x over x minus 1, right? Let's say we're trying to find the relative extrema on this entire function, not just some intervals, but the entire function, right? So in this case, what we are going to do is we are going to take the first derivative, right? So we have to say where y prime is 0 or doesn't exist, right? Or is d and e, right? So looking at this function, right? In order for y prime to be 0, right? Actually, in this case, just so we save ourselves a bit of work, let's say y prime is equal to this, right? So there'll be some function which generates this as its derivative. So let's just say that y prime is equal to this. So in order to find the extrema of the function, we have to find where y prime equals to 0 doesn't exist. So y prime is equal to 0 at so y prime is equal to 0 at y prime is equal to 0 at 0 and 2, and it is equal to it is like doesn't exist. Or sorry, I muted there for a second. It doesn't exist when it doesn't exist when when x equals 1. Sorry, I got confused, right? And then so just because we don't know how to take the derivative of something like so yet, right? 1/2 x squared minus x minus ln x minus 1, right? This will, if we take the derivative of this function, right, we will get this y prime. But just to avoid having to do that, right? Or essentially, let's actually forget about it. We don't even need this. I don't know why I'm doing this, but essentially the list of values that we formed are for our critical numbers are 0, 1, and 2. So the numerator is 0 at x equals to 0, and it's equal to 2. It's equal to 0 when x equals to 2 as well, right? So, and then 1 is when the denominator is 0, so it will essentially not exist. So now what we have to do is we have to find the second derivative. We have to find the second derivative of this, right? So for the second derivative, we will use quotient rule, right? So quotient rule essentially tells us, right, that take the derivative of the first one, so 2x minus 2 times x minus 1, right, minus x squared minus 2x all over x minus 1 squared, right? So all over x minus 1 squared. This is what it'll be, essentially, right? So essentially, so if we simplify this, right, this can be simplified to 2x squared minus 4x plus 2 minus x squared plus 2x, right, all over x minus 1 squared, right? And then if we take the if we then simplify this, right, it'll essentially so if we then so if we then take the derivative, right, then we simplify this, it'll be it'll simplify to 1, and then 1 plus 1 over x minus 1 squared. And essentially what the second derivative test will tell us is that based off of this, we can evaluate essentially which ones are going to be relative maximum, which one's going to be relative minimum, right? Because if this represents concavity, and then if the double derivative is positive, it's concave up. Otherwise, it is concave down. So what this represents is the fact that if this is positive, it's going to be a relative minimum, but if it's negative, it's going to be a relative maximum, right? So in this case, if we plug in 0 here, it's going to be 1 over 1, which is going to be 1, which is going to be 2. So it's positive, right? So it's going to simplify into, it is going to be a relative minimum. But if we plug in 1 into here, right, if we plug in 1 minus 1 is 0, 1 over 0, like the derivative at that point doesn't exist. So essentially, so the derivative at that point doesn't exist. So what that means is that it could be an inflection point or something of that sort, and we don't know, essentially. And then for 2, if we plug in 2 in, it's also going to be positive, so it's also relative minimum. So in this case, because we know that all functions have to have a relative maximum, we can, because of EVT, we know that over an interval, a function has to have a maximum. We can say that 1 is actually the maximum, even though we say that it doesn't exist. But that's the second derivative test, right? Based off of concavity, we say whether it's a relative maximum or a relative minimum, right? So now let's move on to a theorem called Rolle's theorem, right? So what Rolle's theorem tells us is that if we let f be continuous, so the extreme value theorem states that a continuous function on a closed interval ab must have both a minimum and a maximum on an interval, and both of these values, however, can occur at endpoints, right? So Rolle's theorem gives the conditions that guarantee the existence of an extreme value in the interior of a closed interval, right? So if f is continuous on the closed interval AB and differentiable on the open interval AB, if f of A equals to f of B, then there is at least one number in C in in the interval AB such that the derivative of C equals to 0, right? So something like so. So essentially what this is saying is that between two points, right, that are on the same axis, right, so the slope between them is 0, then there is some point, right, if we draw out a function like so, there's going to be some point in here where the derivative is 0. So like so, right? So there's going to be at least one point where something like this happens, right? And in fact, if we think, this is Rolle's theorem, right? So Rolle's. Yeah, so Rolle's theorem is actually an extension of the mean value theorem, right? So the mean value theorem is Rolle's theorem is just a part of the mean value theorem. But the mean value theorem is something very similar, right? So Rolle's and MVT, what MVT tells us now is that if we have 2 points, right, these 2 points will have some average slope, like so, right? Yeah. So it'll have a slope like this, and then if we draw a function out between this time, then there is some point where we draw a tangent line, and it will be parallel to this average slope, or it's going to be like the same, or just for clarity, right? It will. Yeah, I'll use this a lot, but you can see what these theorems essentially say, right? Essentially, if we have 2 points and they'll have an average slope between each other, and so between this, it's an existence function which says that there exists a point on there where the slope is equal to the average slope, right? So these 2 theorems are extremely important, and we'll actually do one practice problem. So this will be problem number 7 of the day, right? So yeah, these 2 are very simple theorems, but just make sure you remember them, and just remember MVT. Rolle's is just a little core. It's just a little part of it, right? But MVT is the big one that you have to remember, right? So essentially, how it's going to appear as a question on the AP test is they're going to say what value of, so you're going to have a function y equals to x squared minus 2x. Something like so. So what value on the interval 1/2, what C proves MVT? So which one will prove MVT? So in order to solve this, what we're going to have to do is we're going to use the average slope formula, right? Which is simply f of a, right? f of b, right? Plug in 2 squared minus 2x is 0, right? So this will be 0 minus, and then if we plug in 0 into here, right? If we plug in 0 into here, 0 squared minus 0 is just 0. So all of this, so 0 divided by 2 minus 0, which is 2. So this is just 0. So there is going to be some point on this thing, MVT tells us, and this is actually Rolle's theorem, but in this case, MVT will tell us that there is some point on this interval 0, 2, where the value will be equal to, the derivative will be equal to 0, and we have to prove where that value of, we have to prove MVT using that. So y prime of this is equal to 2x minus 2, right? So now, if we solve for this being 0, right, 2x minus 2, we get that x equals to 1, right? So at x equals to 1, which lies in between this interval, the slope is 0. So this means that essentially we have proven MVT. And this will be the type of problems. It'll be find some C that proves MVT or something like that. but you're just essentially going to find the x value where the conditions for MVT is actually chosen, right? So MVT is simply an existence theorem, but on the actual AP test, a question could be prove that the MVT existence, find the value that MVT is proving, or something like that, right? So now let's go on to increasing and decreasing functions and the first derivative test. So we've already gone over the second derivative test, which tells you which one is going to be, like which values are going to be extrema, like relative maximums, and which ones are going to be relative minimums. So for increasing and decreasing functions, right? So a function of f is increasing on an interval when for any two numbers x1, x2 in the interval, x1 is less than x2 implies that f of x1 is also less than f of x2. And it's decreasing when f of x1 is greater than f of x2, right? So essentially increasing as x moves to the right and then the graph moves up, and it's decreasing when the graph moves down, right? So for example, right, the derivative is related to the slope of a function. So it's decreasing when the derivative is less than 0, constant when the derivative is 0, and increasing when the derivative is greater than 0, right? So in order to actually do this, we will be using a thing called the first derivative test. So after we've determined the intervals of the function, if we've determined the intervals on which a function is increasing or decreasing, it won't be difficult to locate the relative extrema of the function. So, for example, the function x to the 3 minus x squared, or minus 3 halves of x squared, has a relative maximum at the point 0, 0, because f is increasing immediately to the left of this and to the right of this, right? So essentially, what the first derivative test will tell us is essentially an alternative to the second derivative test. And essentially, if we look at values directly to the right and directly to the left, and we see what the derivatives are, in fact, this is where we use sign chart, we can see if it's increasing or decreasing, and it doesn't have the limitation where the second derivative might not exist. So let's do practice problem number 8. So practice problem number 8 will essentially be we are going to so y equals to x cubed minus 2x, right? Actually, this works well. X cubed minus x, right? And we are asked to find the intervals where the function is increasing and decreasing, and also which ones are relative minimums and maximums. So what we will do with this is, with the first derivative test, what we can do is we will essentially make a sign chart. So let's practice making a sign chart. So with this, we'll say that f of x, right, we'll have one for f prime of x, so we'll have one for f prime of x, right? And essentially what we are going to do is we are going to choose the values, right? So if we factor this, right, we have negative, or why did I put negative 8? I keep doing this where I write the infinity like this. We're gonna have negative infinity, and then we're gonna put all the critical numbers, right? I won't make you do this derivation right now, but it should be pretty easy to find out what these values will actually be. So we'll have negative infinity, negative 1, 0, 1, and then infinity, right? And essentially what we're going to do here so actually let's not do this. Right? So essentially what we're going to do is we're going to be looking for the derivative at these values, right? So we're going to see if it's increasing or if it's decreasing, right? So essentially, if we solve for y prime, right, y prime is going to be equal to 3x squared minus 1, right? And then essentially, if we solve this, right, we'll get that. If we solve this when this equals to 0, we will get that x equals to plus minus square root 1/3, right? So these are the values where it equals to 0, and for values like if we plug in negative infinity into this function, this x squared term will always be positive, right? So yeah, so this x squared term will always be positive. So in this case, right, it's going to this is going to be up, right? So up like so, and then yeah. So and then also if we plug in negative infinity into this function, right, it's going to be like super low. It's going to be like low, right? So it's going to approach negative infinity, and then at -1, right, it's going to be 0. And then at 0, it's also going to be 0. So for all these values, it's going to be 0, right? And then in between this, right, if we have like -3 and plug this into here, right, -3 squared minus -3, right, it's still going to be, plug in values here, right, it's still going to be negative in between this. So negative, but it's still increasing. And then at -1, if we plug -1 here, right, it's going to be 2. So it's still going to be increasing, right? But then when negative square root of 1/3 comes here, right, then it is going to flip to negative, right? So it's going to flip to negative like here. And then by the time it's back, it's also going to be increasing once again, right? So it's going to be dipping for the short value here. So based off of this sign chart, right, she's going to be positive here, negative here, positive here, and infinity here, right? Actually, no, I don't know why I put 0. Yeah, so it's gonna be something like so, right? So it's increasing on the intervals from negative infinity to negative square root 1/3, and it's gonna be decreasing. Sorry, and it's gonna be increasing. And between negative 1/3 and positive 1/3, it is going to be decreasing. And then on the interval from positive square root 1/3 and infinity, it is going to be increasing once again, right? So based off of this, right, we can determine the intervals, and then we can determine the extrema. So the first derivative test, if it's going from increasing to it's still increasing, right? So this is going to be a relative maximum, right? If it's increasing, right? And then this is going to be a relative minimum. This is going to be a relative maximum, right? So yeah, that's essentially how it's going to work, right? This is going to be relative maximum, and it's going to be relative minimum. So that's how we apply this the first derivative tests, right? So now with concavity, right? Concavity is essentially, like I said, the second derivative determines concavity. So if we have right, where we have a double derivative, right? If this double derivative is less than 0, right, it's going to look something like this, right? So it's going to be like this, where it's concave down, right? It's like scooping downwards. If it's like, if y double prime equals to 0, right, then it's going to be at a point where it's like scooping downwards, but it's going to be what we call an inflection point, where the concavity changes. So something like that, right? And then now, if y prime is greater than 0, then it's going to look something like so, right? So essentially, you can see the direction in which it's scooping, and that's essentially what it's going to look like. And we already went over the second derivative test, where if it's the derivative is positive, right, clearly it's a relative minimum. And if the second derivative is negative, it's going to be a relative maximum, right? And if it's an inflection point, then that's just a fake. It's a fake extremum. So personally, I prefer the second derivative test, but that is essentially, that's essentially how it's going to work, right? So now let's talk about limits at infinity, right? Since we haven't really covered that, right? And yeah, so limits at, so let's actually talk about, let's talk about limits at infinity, since, so essentially what we will be discussing here is the end behavior of a function on the infinite interval, right? So essentially what this means is that as we approach to negative infinity, it'll approach some value, and as we approach to infinity, it'll also be approaching some value, right? So the limits as we approach infinity will be looking something like this. Limit as x approaches to negative infinity, and also limit as x approaches to infinity, right? And let's go over and this is essentially going to be how we evaluate horizontal asymptotes, right? So if this, so essentially if this equals to some L, right? And this is what we call end behavior, right? So if either of these is equal to some L, that means it asymptotes at infinity. So it's asymptoting. It's a horizontal asymptote, right? So essentially what it means is that so if it approaches some value, that means it's a horizontal asymptote. If it's positive infinity or negative infinity, it increases without bound. There's no asymptote. But essentially, the way that we are going to do limits at infinity is, let's do a practice problem on this, right? Practice problem number 10 of the day, right? So this is going to be, let's say we have a function like so. Right, let's say we're trying to evaluate the limit as x approaches to infinity of x cubed plus 2x squared plus 8 over 3x cubed plus 2, right? So let's say we're trying to evaluate this. Essentially what we're going to do is we are going to, what you're going to want to do on the AP test, if you see something like this, is that you are going to so if we have sorry. If you have something like so, right? What we are essentially going to do is we are going to want to take the x cubed out, right? And what this is going to leave us with is we're going to have 1 plus 2 divided by x plus 8 divided by x cubed, right? Or something like so. And then now if we take out a 3x cubed, right? This is going to be 1 plus, it's going to be 2/3 over x cubed. Yeah, it's going to look something like this, right? So 2 over 3x cubed. But essentially now what we're going to consider is the limit as 2 over x approaches to infinity or negative infinity. If we have that in the denominator, it is always going to approach 0. So all of these shenanigans with x's in the bottom are all going to turn into 0, right? So essentially what this means is that these will all cancel out with the other stuff, right? And so in the end, right, yeah, and also these x cubes will cancel out because we've taken them out. So in the end, what we'll have a limit as x approaches to infinity of 1/3, which is simply equal to 1/3. So that is how we evaluate like a horizontal asymptote or something like that. So let's say we were looking for the horizontal asymptote of this function. Now we know it, right? In pre-calc, you learned there's a weird concept, but now in calc, it is much easier to do this. And we're actually gonna end off today by talking about and vertical asymptotes are pretty obvious as well, right? Where it doesn't exist. So and also there's no holes. Where the function itself doesn't exist, it'll be a vertical asymptote. But for horizontal asymptotes, you have to use a limit as it approaches to infinity, and this is how you actually work through solving it, right? But now, for the last concept of the day, we are going to be covering optimization. And essentially, optimization is essentially going to be an applied minimum or a maximum problem, right? So essentially what this means is you are going to have like a function between two variables, right? And essentially you are going to have to determine like which one, for example, if we have a box and it's determined between like variables, you're going to need to determine what the maximum area is or what like the minimum area is. So problems like these also appear on the AME. So it's like on the AMC, AME, things like that, math competitions. But essentially what we're going to do is we are going to use what we learned about extrema in order to solve such a problem, right? So let's actually start off with a simple optimization problem. So let's say we're trying to... So this will actually be the last problem of the day, right? So today's topic was actually pretty short because we were just applying things we know about derivatives to like graphs, to like theorems, new theorems, but essentially the lesson for today was actually pretty short, right? We only did 11 we did 11 practice problems, and like yeah, this lesson will be under an hour. So yeah, so this is actually one of our shorter topics, and hopefully like it wasn't too boring. Next time we are gonna go over like integration, right? But like let's get into it. So let's say we have like a wall like so, right? This is like the wall to our barn, right? And then on this side of the wall, we have like a fence enclosing some crops, right? So there's some crops here, right? We're cultivating some crops. And we're trying to find, we have a set amount of fence, right? So we only have 36 meters of fence. And our goal is to evaluate the maximum like area of land that we can encapsulate, right? So what we are going to do is the maximum area, right? We are going to define a variable called we essentially, because 36 meters, right? So let's say that the value of this side is x, just so we can represent this as a function and then use optimization. So let's say the length of this side is x, right? And so then thus, because of rectangle properties, this side will also be of length x, and this side will be of length 36 minus 2x, right? So this, essentially what we are going to do is we want to find the absolute maximum of the following function, right? Y is going to be we're going to do something similar, right? Where we have area is going to be equal to this first side multiplied by the second side. Like so, right? And so if we simplify this, 36x minus 2x squared, right? So now, in order to find the maximum, right, we're gonna have to look for critical numbers. So the first thing we're gonna have to do is determine an interval where we're gonna find this absolute maximum, right? So it should be pretty obvious, right, that either side can't be 0. So the maximum that this side x, it has to be on the interval, right? X is its own side, so it'll be like open interval of 0. And then for this side, for this longer side, right, is going to be an open interval of 18. Because if it's anything more than 18, that is it's a negative side. So something like so is going to be our interval. So if we are determining critical numbers, right, what we're gonna have to do is we're gonna take the derivative, right, which will be equal to 36 minus 4x, something like so, right? So then in this case, right, x equals to 9, right? That is going to be the critical number that comes out of this. And also, there's no place where it's never equal. So our only ones that we actually have to check is now using our critical numbers. So 0, 9, 18, right? Of course, you can use first derivative test here, second derivative test, anything you want. But in this case, we're going to go back to old-fashioned and just plug it into our area function. So if we plug in 0 into our area function, right, we'll get 36 minus 2. We'll get 36 minus... So if we plug in 0, it'll just be 0. If we plug in 18, right, it's also just going to be 0, right? Because 36 times 18 minus 2 times 18 times 18, that is just... 2 times 18 times 18 minus 2 times 18 times 18, which just equals to 0. So these both are 0. But now if we plug in 9 into this, right, then what we will get is that it'll be 36 multiplied by 9 minus 2 times 9 squared, right? So this is going to be equal to 2 times 9 squared, which is equal to 162 meters cubed, right? So this is actually, so 162 meters cubed is going to be our maximum area that we can encapsulate. So this is what a typical optimization problem is going to look like. And with that note, we are going to leave off today. Hopefully you enjoy this lesson. Next time, we are going to be looking at integrals and integration. Our next class is Saturday, so take a nice break from doing calculus for a little, and hopefully you enjoyed, and we'll see you in the next one.